There is this completely other world of mathematics, different from school maths. And if you are preparing for mathematical Olympiads or ISI and CMI entrances, then you have already seen this world. And many students ask me, in fact, parents asked me, how do I get started in this journey? There is no one right answer, but in most cases, you should start with a beautiful problem. In fact, make it a habit to do one beautiful problem every day. You don't have to complete the problem. You can just think about it. Jot it down in your notebook, make a few diagrams, make a few use cases. It's even better if you can communicate with someone, talk to a friend about that problem. If you are an internal student at chinta.com, then you can obviously talk to your peers in the Math Olympiad program or ISI-CMI Entrance program. Check the link in the description for more details related to such courses. But today, we will talk about one such fun problem. These problems require a bit of ingenuity, a twist. This problem says that there are 11 line segments that make a loop. So let me make a loop with 5 line segments. 1, 2, 3, 4, 5. A closed loop with 5 line segments. Like this, you can make a loop with 11 line segments. I'm not going to draw the entire loop, but you understand what a closed loop is, right? So this is another closed loop. Like this, make a closed loop with 11 line segments. And then draw a line that passes through not the vertices. So these are the vertices. These are the vertices, not the vertices that passes through the edges, the line segments. So for example, I can draw a line like this. Of course, this line cuts 2 edges. Similarly, I can draw a line like this for this particular loop. So this one cuts 1, 2, 3, 4. 4 of the edges. Now the question says, here is the question. Can you draw a line segment that cuts all the 11 edges? Can you draw a line that cuts all 11 edges and does not pass through vertices So the fun fact is, and this is how you can start thinking about this problem, you can actually draw closed loops in a zigzag manner such that a line is possible that cuts many of the edges. Let me show you one such case. Let's draw a closed loop made out of edges. But I'll draw it in a very clever way. here you go. These are the vertices. Maybe I can mark the vertices in red. These are the vertices. And these are the edges. And the question is, can I draw a line that cuts through all the edges? So let's see. I think I can cleverly do it if I'm careful. Here is a line. Here is a line that cuts through all the edges. And how many edges are there? 1, 2, 3, 4, 5, 6, 7, 8. Now at this point, I'll make a comment on how to think about how to use this sort of problems. The best way is not to write or not to look at hints or solutions. I mean, you can look at hints, but never look at solutions. So if you are a student trying a problem like this, a fun problem like this, then first try drawing some pictures and try to see a pattern. Try to see a pattern. Do you see a particular event, a particular picture emerging all the time? Maybe that is a hint towards the more general case. So in this problem, for 8 edges, there is a closed loop such that there is a line that cuts through all the edges. This is the closed loop, the one that I have drawn. Is it possible for a closed loop with 11 edges? It's possible for a closed loop with 8 edges. Is it possible for a closed loop with 11 edges? So here, we're going to use a mathematical tool called parity. Parity roughly means evenness and oddness, though it can mean something very different depending on the context. But let's, for the moment, think about evenness and oddness. Now, if there is a line that cuts through all the edges, let's draw the infinite line. Okay? So the infinite line divides the entire plane into 2 half planes. The half plane 1 and the half plane 2. Now notice that whenever this line cuts an edge, one of its endpoints is in one of the half planes, the other endpoint is in the other half plane. One of the endpoints is in one half plane, the other endpoint is in the other half plane. So corresponding to each point in half plane 2, there is a point in half plane 1. So for example, for corresponding to this point in half plane 2, we have this point in half plane 1. Similarly, corresponding to this point in half plane 1, we have this point in half plane 2. Corresponding to this point in half plane 2, we have this point in half plane 1. And corresponding to this point in half plane 1, we have this point in half plane 2. Do you notice something? That this line, the argument that we just made, the argument says that this line divides the vertices into 2 groups. The vertices in half plane 1 and the vertices in half plane 2. And not only that, the vertex there, the number of vertices in half plane 1 should be exactly the same as the number of vertices of half plane 2 because they are matched up. So what can you say about the total number of vertices? If you could halve the number of vertices into two groups of equal size, what can you say about the total number of vertices? This is the challenge question I have for the viewers. What can you say about the total number of vertices? And why that would mean that we cannot have 11 vertices. A closed loop with 11 segments have 11 vertices. Why can't we have 11 vertices? Problems like this requires a bit of time to meditate. This is like a meditation. So you should take time, do some little scribbles in the notebook and think about it. There is no rush. Just think about it. And then if you can find the reason, that will bring you immense joy and happiness. So thank you for watching this video. If you like this kind of stuff, please feel free to subscribe and like the particular video. It will encourage us to make more such content. Keep on doing good mathematics. Stay well, and I'll see you in the next one.